Is 3.4. It's called Look What's Trending. Hashtag because of chemistry. It says, don't follow a trend, follow your heart. Isn't that sweet? So the learning goals for this are students will understand the relationship between subatomic particles and periodic trends, that you'll understand the relationship between the periodic table shape and periodic trends, and that you'll be able to predict properties based on periodic trends. So here's what we know. There is a consistent pattern of protons, neutrons, and electrons in elements. The periodic table shows trends in atomic structure, and that chemical families have similar properties. So here's what we learned in the lab. We learned that elements in the same column have the same number of outer electrons, and elements in the same row use the same outer electron level, so they have the same valence electrons. So the proton-electron interaction, we talked about it briefly before, but atoms are held together by what's called the electrostatic force. And what that is that's the attraction between any two things that have an opposite charge. Protons are positively charged, electrons are negatively charged, and they attract. So that's the whole idea of opposites attract. Okay, Coulombs Law is what governs these attractions. And then Coulomb's Law is actually called F equals K Q1 Q2 over D squared. This is actually a formula that you will learn and you will use in physics. But conceptually, it helps to understand it in chemistry. So you need to be able to kind of use this later. We're not going to use this particular formula this year, but you do need to know that the larger charge there is, the more likely they are to attract. The smaller distance they are, the more likely they are to attract or repel, the greater the force is. So we're going to use it conceptually. And we're going to use it conceptually in what we call effective nuclear charge. Effective nuclear charge is what we use because it's very, very, very difficult to use Coulomb's law in something like uranium, in which there are 92 protons and 92 electrons. The math in it would just be absurd. So what we have to do is we actually simplify it by using a model which is called the effective nuclear charge. The effective nuclear charge is an estimate of the average force that's exerted between a proton and an electron. Okay? And in order to use the effective nuclear charge, the first thing that we need to do is we need to know something about what's called electron shielding. So if you were to look at one of these outer electrons, it doesn't experience the full attraction of the nucleus because there are negative charges in the way. So this charge right here doesn't experience the full 12 protons of the nucleus because there are 10 electrons in its way that get in the way of its attraction. So these electrons, we say, shield part of the positive charge of the nucleus. So shielding electrons are the number of electrons in the closest previous noble gas. So for example, if I am, let's say that I'm in carbon, the previous, so I go left, noble gas means I go left and then I have to come up, would be helium. So the number of shielding electrons that carbon has is 2, because that's how many electrons there are in helium. The effective nuclear charge is calculated as the atomic number, which is the number of protons, minus the number of shielding electrons. So let's look at this. So the first thing it says, looking at the equation for Coulomb's law, which will have a greater impact on the attraction between the nucleus and an electron? Doubling one of the positive charges or doubling the distance. So if you were to look at this, F equals K Q1 Q2 over D squared. Now if I were to double one of these, let's say I doubled Q2, what that would do is if I multiplied this by 2, I would multiply the other side by 2. So that has a relatively large impact. If you double the charge, it doubles the force. But if you were to double the distance is a squared term. So if you were to double the distance, that ends up being squared. It ends up being 4d squared. The force changes by a factor of 4. So because distance is a squared term, it has a much greater impact on the Coulomb, or on the attraction between the nucleus and an electron. What that means is that electrons that are close to the nucleus have a much greater attraction than electrons that are further away. Next, we have a proficient example. It says calculate the effective nuclear charge for fluorine and the effective nuclear charge for chlorine. So we'll look at fluorine and chlorine. Now, in order to calculate the effective nuclear charge, you need to find its position on the periodic table. The first thing that you should realize is that if you look at fluorine, fluorine has an atomic number of 9, because if you were to look at the periodic table, it has a 9 for its atomic number. Chlorine, on the other hand, which is right below fluorine, actually has 17. So if you look at this, the next thing we need to look at is the number of shielding electrons. Now for fluorine, if we go to the left, we go oxygen, nitrogen, carbon, boron, we keep going until we get to a noble gas, then the first noble gas we get to is helium. And helium has 2 valence electrons, which gives fluorine an effective nuclear charge of 7. Chlorine, on the other hand, if we go from chlorine, we go left to sulfur and phosphorus and silicon and aluminum. The next one that we get to a noble gas is neon, which is 10. So 17 minus 10 is 7. So if you look, chlorine and fluorine have the exact same effective nuclear charge, which is significant because they are actually similar chemical properties because they are both halogens. We have a scientist is attempting to isolate 2 separate isotopes of helium, determine whether the attraction of the nucleus for each of the isotopes is different when placed next to a large negatively charged rod. So I have a negatively charged object, I have helium-3, and I have helium-4. And this is a tough question because it says, okay, determine whether the attraction is different when placed next to each other. So the first thing that we need to do is we need to say, okay, we're probably going to need to charge these in order for something to occur because both of these are neutral. So the first thing that if you said, no, there is no difference, they are not attracted because they are both neutral, that would be a perfectly valid answer to this question. Now if you said, hey, we charge these things, and if we charge them, they're both attracted to this thing at the same force of attraction, that would be correct as well. In actuality, if you charge these things, they would have the same force pushing on them, but because this one is so much heavier, it doesn't move nearly as much as helium-3 does. So even though you were to push them with the same attraction, the helium-3 would move much quicker and get there much faster. It's like pushing a large van versus pushing a Mini Cooper. Okay, it's just a big difference in the mass. When we look at the trend for effective nuclear charge, there's a definite pattern that we can see. So the first thing we do is we start with the lowest atomic number, which is hydrogen. And when we have hydrogen, you've got the nucleus, and then you've got 1 electron that's around it. The effective nuclear charge of hydrogen, there are 0 shielding electrons, so you would say 1 minus 0, and the effective nuclear charge of hydrogen would be 1. When we do the same thing for helium, we just add a second electron. But neither one of these electrons at this point is a shielding electron because there's only the 1 orbital, there's no inner orbital. There are 2 protons in helium, 2 minus 0 gives an effective nuclear charge of 2. So you see the general pattern as you increase the atomic number, generally speaking, the effective nuclear charge increases as well. But when we go to the next one, it gets to be just a little bit different. Whenever we add the next element, the next element is lithium. We add another orbital, so we're no longer just talking about the 1 orbital, we're talking about the 2 orbital at this point. So now when you draw it this way, you can clearly see that there are inner electrons. These right here are the shielding electrons that actually disguise part of the charge. So although we have 3 protons in lithium, I now have 2 shielding electrons, which actually reduces the effective nuclear charge to 1. So you see a general increase in the effective nuclear charge, but occasionally you have these things where it drops back down. When it drops back down, it's because you're adding another layer or another orbital to the atom. So this right here, you can see this trend. As the atomic number goes up, generally speaking, you see an increase in the effective nuclear charge, but then you see a drop. You see an increase, and then you see a drop. You see an increase, and then you see a drop. What that is showing is that's showing the trend of adding another orbital in. Because as soon as you add another orbital to the outside, you vastly increase the number of inner or shielding electrons that you have. So for atom size, it's really hard to define the atom size just because of where does the atom start and where does the atom begin. Generally speaking, when we talk about the classical atom size, we're including the protons, neutrons, and electrons. And this is where it gets tricky is because the electrons are never constantly in the same place. According to the classical model, they are stuck in these particular orbitals. But the problem is if this is a hydrogen atom, the electron could be here, 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 or here, depending on the energy of that particular hydrogen atom. Generally speaking, we refer to what the classical atom size is as the size in the ground state. So in this particular case, it would be a hydrogen would be 0.529 angstroms, or 5.29 times 10 to the minus 10th, or 10 to the minus 11th, which represents what we call the Bohr radius. Okay, the atomic radii, if you were to look at the trends for atomic radii, you would notice that as you move down the periodic table, you increase the distance by adding another level of electrons. So in other words, as I go down the periodic table, here's my first one, hydrogen. When I go to lithium, it's the same thing, but I add one. When I go to sodium, it's the same thing, but I add another layer. It's the same thing, but I add another layer. So as you increase, as you move down the periodic table, the trend is increasing. The atomic radii increases because you're adding another layer. Now, as you move from left to right across the periodic table, you actually see a decrease in the atomic radii. And the reason for that is this. You've already established, let's say if we were to look at lithium. So lithium has its two electrons right here, and it has another electron right there. Now, the reason why the atomic radii shrinks as you move across the periodic table is as you move across the periodic table, you're increasing this Z term, okay, the atomic number. For example, from lithium, it's 3, but for beryllium, it's 4. So you're increasing the effective nuclear charge. But as you move across the periodic table, there is no change in the shield, in the number of shielding electrons. So because of that, the number of shielding electrons remains constant. What that means is the effective nuclear charge increases as you move across the periodic table. And you may be saying, okay, well, if the effective nuclear charge increased, why do I have a decrease in atomic radii? Well, if you were to look at this, if we were to say, here is one atom, and it has a +1, and it's surrounded by, and I want to know what its effect is on this -1 charge, and I have a +2, and I want to know what its effect is on the same distance of this negative charge, you would say that this electron is pulled more to the +2 because it's a greater positive charge. What that does is that actually moves the orbital inward. So atomic radii actually decreases as you move across the periodic table and increases as you move down the periodic table. Ionization energy. Ionization energy is defined as the amount of energy needed to completely remove an electron from an atom. The ionization energy becomes really important. We're going to talk about ions quite a bit later, including naming them and the structure of them and those sorts of things. But if you look at the ionization energy trend, you can also use the idea of Coulombs Law and effective nuclear charge to explain ionization energy. Ionization energy decreases as you move down the periodic table. So the amount of energy required to remove an electron decreases as you move down the periodic table because the electron that you're trying to move is further away. So for example, if I'm looking at helium, or excuse me, let's say hydrogen, if I need to remove this one electron from hydrogen, this positive and the negative charge are very close to one another. Because they're so close to one another, there's a really strong attraction to one another. But as I move to lithium, lithium is further away. Because of the increased distance, the force holding these two things together is not as large. So because of that, it is easier to remove this electron from lithium than it is from hydrogen. When you move further out, now you have potassium. The potassium one is even further away. Because of that, the attraction between the two is even less. So as you move down the periodic table, it becomes easier and easier to remove an electron from an atom. Now, as you look at it from the other perspective, as we move across the periodic table, if we move across the periodic table, we have our orbits. And when we move across the periodic table, what we're doing is we're actually increasing the amount of charge. So I'm going from +1 to +2 to +3. Well, if you do that, as you move across the periodic table, you're increasing the amount of charge that is affecting this one electron that you're trying to remove. So if you're increasing the amount of positive charge, it will actually it'll increase the force between these two and make it much more difficult to remove an electron. So thereby it increases the ionization energy. So the trend that we see because of Coulomb's law and effective nuclear charge is that there's a decrease in ionization energy as you go down and an increase as you go across. Electron affinity is defined as the ability of an atom to capture an incoming electron. So it has to have access to the positive nucleus. If you have kind of a free electron, the only way that it's going to be captured by an atom is if it's somehow attracted to the positive nucleus. So the trend that we have for electron affinity, once again, can be explained using Coulomb's law and effective nuclear charge. Electron affinity increases as you move across the periodic table. And that should make some sense because what you're doing is you're increasing the positive charge. As you increase the positive charge, this free electron is going to be pulled more towards the atom. So electron affinity increases as you move from left to right. Now electron affinity actually increases as you move from bottom to top as well, because if you have multiple layers of electrons to go through, it is less likely that this electron would feel the full effect of the nucleus because of effective nuclear charge. So electron affinity, or access to the nucleus, actually increases from left to right and increases from bottom to top. Electronegativity is very similar to electron affinity. It's the measure of an atom's ability to pull an electron, but instead of capturing a free electron, it's talking about sharing an electron with another atom. And once again, it depends on Coulomb's law and effective nuclear charge. So we have the electronegativity trend. It is the exact same one as the electron affinity. Like I said, the only difference between the two is whether it's capturing a free electron or whether it's pulling a shared electron closer to one atom or the other. So now we go to the developing B1. It says what elements would behave in a similar manner to calcium. So we're trying to figure out what the pattern would be as far as how it behaves. Remember, whenever you're talking about an element that has a behavior, you're looking for elements that have the same column because they have the same or similar effective nuclear charges. So you could pick anything that was in group 2. Okay, for example, you could have barium, or you could have beryllium, or you could have anything that's in that particular column. Now, the closer you are in terms of atomic mass, the better. So strontium should be better than barium, but they both have similar chemical properties. Next, we have proficient B2. It says in the fifth period, all the outer electrons occupy the same energy level, although they have different atomic radii and reactivity. What is the relationship between atomic radii and reactivity? So if you were to look here, if you were to plot reactivity, this element and this element are extremely reactive. Xenon's not reactive at all. Okay, so if you were to kind of plot the reactivity, it kind of goes like this, or a quadratic shape that you see in math class. So that's what you have in terms of reactivity. Now, if you were to plot the relationship between atomic radii actually starts out really large, and it actually decreases as you move across. Now, what is the relationship between these two? And the answer is there really is none. And sometimes that's hard for people to understand, is there's not a relationship between these two things. It doesn't matter how big an atom is in terms of its reactivity. It depends on what its electrons look like, not how far they are away. And finally, it says using the clear method, describe why magnesium and copper have approximately the same atomic radius. Now, these are in different periods and they're in different groups. Copper is a transition metal that appears to be in group 3. Magnesium is in group 3 and copper appears to be in group 4. So if you were to look at that, they're in very different layers. So you have magnesium, which has 3 layers of electrons, and you have copper, which has 4 layers of electrons. So the question becomes, how can these be approximately the same size? And it all has to do with a combination of Coulomb's law and effective nuclear charge. Although this only has 3 layers, it only has 12 protons. The 12 protons exert kind of a minimal pull on the outer electrons. Now, if you were to look at copper's 29, which has over twice the number of protons, and therefore has a greater force that's exerted on it. So because of that, even though this has a 4th layer, that 4th layer is actually moved closer than this one where the 3rd layer is kind of expanded out.